All right, this is what we're going to do. We've been looking at one-dimensional kinematics. And if we can do, and you guys are doing really well with that, so if we can do one-dimensional kinematics, two-dimensional motion, like for example this long jumper flinging herself up in the air in two-dimensional motion, you can, if you could look at it as a horizontal component and a vertical component of motion, if we can do one-dimensional motion, we can do two. And so we're going to talk a little bit about that in this brief screencast to get a sense of how you can just extend what you already know in one dimension into two dimensions. All right, now just some basic concept vector stuff. Just this might come up a little bit more later, but if you look at, let's say you have a point here, this position, and you can represent that position as a vector from the origin. A position can be represented as a vector. This is vector R1 representing position 1. And it moves along some path to another position, position 2, which could be represented by this position vector. So this vector represents position 1, this vector represents position 2, and delta R is the displacement, which takes you from position R1 to R2. And in terms of vector language, R initial plus delta R equals R final. And it doesn't matter, again, what the path is. The displacement is just the straight line distance between, and the amount of the distance between point 1 and point 2. But this is just kind of showing it in vector language. And similarly, if you have a vector delta R, let's call this your displacement vector, you can break that up into a component that is, and we've done this before, parallel to the x-axis and another component parallel to the y-axis. That makes it easier to add two vectors together when you can add the x components and the y components, as we have already done. So that's basically a kind of a review. Now, in two dimensions, really what we can do, and this is the key to it, is we can treat both dimensions, and this can then be applied to three dimensions, but we take the x direction and treat it completely independent of the y direction. There's a demonstration I want you guys to do at home, and we'll talk about this in class, but it has to do with rolling a ball off a table and dropping a ball at the same time. It will hopefully illustrate the independence of the motion. But basically what we can just say is v average in the x direction and distinguish it from v average in the y direction and treat them separately. So delta x over delta t is vx in the v average in the x direction, and delta y over delta t is v average in the y direction. And instantaneous velocity, again, would just be the limit if we took this is a two-dimensional thing. If you took the delta x and delta y, you made it into one vector, delta r, and took the limit as it approached 0, you get the instantaneous velocity and the instantaneous speed. We won't really need to worry about that too much right now, but those of you in calculus, you can recognize some familiar things. Okay? And the same basic issues are true with the acceleration. You can break it up into an x and a y, and you can also talk about an instantaneous acceleration as you take the time interval down to about 0. So that's basically the idea. Really is just that we're going to look at motion separately in two dimensions, in each dimension individually, and then if we want to, we can recombine them at the end, as you'll see in the example we're going to do in a few minutes. Okay? Just for funsies, which of the following objects can't be accelerating? Okay? We'll look at the three questions. Can an object moving with a constant speed be accelerating? Well, it can, because accelerating means your velocity is changing. The question is, can you change your velocity if your speed is constant? And yes, you can, if you are changing direction. So something in orbital motion at a constant speed is constantly accelerating, even though the speed isn't changing. So that's an interesting issue that we'll look at when we look at things like circular motion. So an object moving along a curve, its direction is changing, which means its velocity is changing, and therefore it is accelerating. So the only one that isn't accelerating is an object moving with a constant velocity, not constant speed. Okay. In an automobile, which of these cause an acceleration? the gas pedal, the brake, or in the steering wheel? Well, based on what we just said, they all do. A gas pedal can speed you up, a brake can slow you down, a steering wheel can change your direction. All those things are changes in velocity, so all those things are accelerations. Okay? Now, again, if we are going to go into 2 dimensions, and again, it's basically sort of review, the average speed in going from this point to this point is not going to be the same as the average velocity, because the average speed is the total distance traveled over the time. This distance, if you look at the half of a circumference of a circle, is going to be about pi times 10 meters. So it's going to be about 30-something meters in 15 seconds. So your average speed is going to be covering length at about a little over 2 meters per second. However, if it's velocity, all you're looking at is the displacement from beginning to the end of the motion, which is 20 meters in 15 seconds. So it's only about 1 1/3 meter per second. So this is how you would look at the difference between speed and velocity in 2 dimensions if a motion is undergoing a path sort of like this. Okay? Now, what we're going to look at in detail is projectile motion. It's a good example of 2-dimensional motion, and the horizontal and vertical motions are completely independent of each other. In the horizontal direction, you have an x if you launch something at an angle like this, the horizontal part of the motion, and we'll talk about this, never changes if you assume air resistance is negligible. So really what you're looking at is a horizontal motion that's moving at a constant rate, while a vertical motion is superimposed. So in this case, you throw a ball up in the air at the same time as it's moving forward. You could basically model this by driving in a car with a tennis ball, throwing the ball straight up in the air. The vertical motion is the exact same if you were just standing on the ground. But to an observer on the ground, you're also moving forward horizontally, so what you get is this parabolic trajectory. You notice these vectors, the x vectors for the velocity, never change. The vertical vectors start up big up, get smaller, turn around, and get big smaller. And the red vector represents the velocity vector as a total vector. You can see I can break it up into a vertical and a horizontal component. And meanwhile, you have a constant downward acceleration due to gravity. And that'll be important because it's a very simple motion. A constant free fall in the vertical direction and a constant velocity in the horizontal direction. Makes it really easy to analyze, as you'll see. Okay? This is something we'll do experimentally, but it's interesting to note that these complementary angles of 90 degrees, that add up to 90 degrees, they all have the same range if you launch the projectile. They have the same range. So a 75-degree angle and a 15-degree angle will have the same horizontal distance covered. And we'll talk about that more later. But a 30 and a 60 would land at the same place. 45 and a 45 would land at the same place. They have the same range of the motion. We're going to look at range of a projectile in just a second. Okay? And this is something we can prove more formally soon. Okay? So, again, now we're just looking at a picture of these are, if we take a projectile launcher and launch a ball, at every given moment the acceleration is always straight downward. Meanwhile, the velocity vector is constantly changing. And that's only because the vertical vector is changing. The horizontal vector is constant. Okay? Now, what we can do is that we can take this initial velocity and break it up into 2 component parts. An x component, which is that constant x velocity, and a y component, which is changing due to the acceleration due to gravity. And we already know how to break vectors into components, so when we're analyzing an actual projectile, it's actually going to be quite easy for us to do. So we're going to start with a couple of examples. Oh, yeah, right. And you remember that if you break the x component, if this angle is the angle between the x component and the vector, the x component would be v0 cosine theta, and the y component would be v0 sine theta, if this is the angle you're choosing. And that usually is the angle we choose. It's the angle relative to the horizontal. Okay? We can use all the exact same kinematic equations. But what we're going to do is for the motion, we're going to write two separate equations, one for the x part of the motion and one for the y part of the motion. And then if we want to put it back together at the end again, we can, and we'll go over that in class. But these are the kinematic equations that we already know. These are just writing them in terms of the x as a variable and writing them in terms of y as a variable. And we'll apply this to the horizontal motion and this to the vertical motion. All right. Almost to our example. So, if you're going to do that, then in the horizontal direction, the x component of velocity is v0 cosine theta 0. So your horizontal distance traveled is just your x component of velocity times the time which you're in the air. Now your horizontal motion has nothing to do with the time you're in the air, because if there's no gravity, for example, you just keep on going and never land. So the time you're in the air is controlled by the vertical part of the motion. And so if you were to look at the vertical part of the motion, I don't really like this. I write plus 1/2 at squared and put in negative 9.8 for g if I'm calling down negative. But these equations are assuming you always call up positive and down negative. You don't have to do that. I usually put a plus in there and an a in here, and if I call the acceleration direction negative, then I put in a negative value for the acceleration. But really, as long as you organize your thoughts, it doesn't really matter, as long as everything is consistent with your directions. Okay? Again, this is all what we just talked about. Vx is constant in our two-dimensional projectile. The acceleration due to gravity, acceleration is due to gravity, and the minus g. And Vy and y behave as if they're in free fall. And we're just going to superimpose the motions in the x and y directions. As you'll see, we'll do a couple of examples, and then we'll continue to pick up the discussion in class. Okay? So here's our procedure, and then we'll do 2 examples. We sketch the projectile path. Make a picture. Get used to drawing a picture. If the initial velocity is not in the x or y direction only, you're going to have to take that initial velocity and break it up into a vertical and a horizontal velocity and treat those individual components as the velocity for the x part of the motion and the velocity initial for the y part of the motion. Treat the motions separately. And we've already discussed these last 2. Remember these. So here's an example. Say you throw a rock with an initial velocity in the horizontal direction of 20 meters per second. And you release the rock 2 meters above the ground. Where's it going to hit the ground? Okay, so remember this. We've been hammering that home. So what I'm going to do is just to write an equation for the horizontal motion, equation for the vertical motion, and see what we get. So here we go. Boom. In the horizontal direction, and this is what I want to find, where I land, x is just Vx times t. I should really say not V average, but Vx average, and which is it's a constant velocity in the x direction. So my position is just 20 meters per second because I'm starting horizontally. And the time, once I have the time, I can find out how far it went. But in order to get the time, all I need to do is look at the vertical motion. The time is completely controlled by the vertical motion. Now, in the vertical motion, it's basically like I just dropped a ball and it fell 2 meters. That's how simple it is. Just happens to be moving at 20 meters per second horizontally, but it's also, I dropped it from a height of 2 meters. So V0 in the y direction, if I shoot it horizontally, is 0. So basically, delta y is just 1/2 at squared. So if I plug in the values, I drop 2 meters, my acceleration rate is negative 9.8 meters per second squared. I solve for the time. It's going to take me 0.64 seconds for the ball to fall to the ground. And therefore, if I plug that back into this equation right here, I'm going to go 12.8 meters. That's as simple as that. I'll do one more example where we launch it at an angle. But now I want you to think about this, and I want you to do this on your own. See if you can determine what the total speed of the ball is upon impact. So I want you to remember the horizontal velocity is constant. But the vertical velocity after it's fallen for 0.64 seconds, you can determine. So what you need to do is take the horizontal velocity You know it already. Add the vertical velocity to it as a vector. Take the vector sum of those two velocities, and you get the total amount of speed by doing the Pythagorean theorem on those two vectors, and you can get the direction by doing some kind of trigonometry. So try it and see if you can get the velocity right before impact. And then we have something to discuss when we pick it back up in class. Okay? So one more example, and then I'm done with my screencast. What if instead you throw the ball up at a 30-degree angle rather than throwing it horizontally? Now, if you do that, then I can't just take the initial speed as 20 meters per second and plug it into either of these horizontal or vertical equations, because it's not going 20 meters per second horizontally, and initially it's also not going 20 meters per second vertically. So what I got to do is break it into a component. The x component, which is v0 cosine 30, and the y component, which is v0 sine 30. So I multiply v0, which is 20 meters per second, times the cosine 30. That means I've thrown it simultaneously at 17.3 meters per second horizontally and upward initially at 10 meters per second. So the horizontal motion equation is exactly what we saw before. How far I go horizontally depends on my horizontal velocity, which is 17.3 meters per second, and that's constant, times the time that it takes. And that's completely controlled by the vertical motion. Now this time, in the vertical motion equation, we have an initial upward velocity. So v0y is positive 10 meters per second. But this is just the problem of I throw a ball up in the air at 10 meters per second. It's 2 meters above the ground. Therefore, when it hits the ground, how much time did it take to get there? So I plug the numbers in, and what I get, if I do it's a quadratic equation, I get somewhere around 2.2 seconds. And now I know the time. I go back and plug it into this equation here, and I find I go a lot farther when I throw it at an angle. It's 38 meters, unless I made some math mistake, which is possible because I just did the problem, and often that can happen, and that's okay. Now, last thing for you guys to try is, all right, what if I want to find the maximum height? And so the hint is, what is the vertical velocity? Not the total. What is the vertical velocity at the maximum height? And then also, think about what part of the motion matters in determining the maximum height. Is it vertical or horizontal? I think it's pretty straightforward which it is. Do you even need the other component of the motion? Okay? So that is my brief introduction to two-dimensional motion, and we are going to call that a wrap.